Okay, so thanks everybody. We're going to have a new session now about information theory and its usefulness and application in trying to understand neural coding and how neurons work. Okay? So the first thing we need to do is start thinking about what's a neuron. You know, a neuron, presumably everybody at least is somewhat familiar, is going to receive an input and it's going to generate an output. The input, we'll call it the stimulus, and the output, we'll call it the response, okay? And so presumably, the response of the neuron is going to tell us something about the stimulus. It's going to contain maybe some information about the stimulus, okay? But so we want to maybe quantify what exactly do we mean by information, but first we want to understand a few things about neural coding. So what is the neuron trying to encode? Imagine if you have this little step current input here. The neuron could be responding with a bunch of action potentials to the amplitude. When the amplitude is high, it responds. Or it could be responding to the change in amplitude. So it just spikes right when the change here happened. So that would be kind of what is the stimulus that the neuron's actually responding to. But then you might also want to think like, okay, the neuron is firing all these spikes and action potentials. They must be containing all the information. But there's been a lot of studies that just show that just the rate of action potentials, the number of spikes per second is all that really matters and not really the precise timing of the spikes. And finally, and I want to say most importantly, but maybe it's not most important, the neuron is not going to usually respond the same every time you present the stimulus. And so what's the degree of variability in the responses? So if you present this step 3 times in a row, you can get a different response every time, or there's some similarity there, or you could get something like this, which looks exactly the same every time. Which, I mean, this is pretty rare. I don't think you would ever see that, but if you do, then that might be telling you even more about the information. And so, because we're using information theory was invented by Claude Shannon, an American scientist, in 1949, and information theory is going to provide us some mathematically rigorous tools for quantifying exactly what we mean by information and how much information is being transmitted here by a neuron. And so he actually invented information theory around the time when the telecommunications network was being set up in the US and around the world, and people were sending messages to each other through Morse code, and they had to sort of encode the messages that they wanted to send with a code, and he needed to quantify how much information is contained in these messages and being transmitted to find the best way to transmit them. And he actually advised against using information theory for other applications that it wasn't designed for, such as neuroscience. But, you know, we're just going to take that with a grain of salt and do it anyway. And we're not the first ones. I mean, it's been going on for a few years now, and so we're going to just talk about quickly a few different ways that information theory has been usefully applied to neural coding. So you could try to estimate, for instance, the information capacity of a neuron. What's the most information it could possibly transmit? And then maybe consider how much information does it actually transmit about different stimuli that it encounters in the natural environment, and quantify the efficiency of the neuron. Is it really using all of its information capacity? Have our neurons sort of evolved over billions of years to be optimal in some way? And we could call this sort of the efficiency of a neuron. Secondly, there's sort of some techniques which we're going to hear a bit more about specifically in this talk, where you could try to estimate the most information the neuron can transmit, as well as, say, the amount of information that a neuron could transmit using sort of an optimal linear model. And then you can compare these two estimates of the information to see maybe if there's some nonlinearities in your neuron, that your linear model isn't capturing, and to help you understand how is the neuron transforming your data. And finally, you can also try to understand what's the limiting temporal precision of the responses and the information contained in them. For instance, you see this nice long spike train. You've got your spikes with sub-millisecond precision. You calculate the information. That's great. But if you jiggle the spikes around and change their timing by a little bit, do you really lose any information? Is there really information in those precise timing of the spikes? Or do you just need, a more coarse-grained response and you still get the same information? So I'm going to start off just by introducing information theory in the simplest possible way that I can. We have to start with probability and entropy. And so hopefully everybody here knows about probability. Hopefully everybody's even heard the word entropy before and is not terribly scared by it. But if you are, just don't think about it. Don't think about those horrible thermodynamics classes in physics you did where they talked about entropy. That's not this. So don't worry. We're going to start with the simplest possible probabilistic experiment that hopefully everybody here has even performed a couple times themselves, a coin toss. And so you're going to toss a coin. The coin essentially has two states, x1 and x2, more conventionally known as heads and tails. And these states have a probability of occurring. If you're playing for money and your friend chooses the coin, you want to know that the probability is actually equal for each state. So the probability should be 50-50, okay? And so let's just assume for now that it is. What's entropy got to do with this? So entropy is a measure of uncertainty. That's all you need to know about entropy right now. And we use the letter H to denote entropy rather than E, because E is usually reserved for energy or something else. But you could also use other letters, but for now we're going to use H. It's not a big deal. And here is the equation for entropy. I'm sorry I have to throw an equation in your face right away like this, but try not to worry about it. All there is the probabilities and this funny logarithm that's base 2, okay? Don't worry about that right now. We're going to see why that has to be there in a few minutes. Just, there's a log on your calculator on MATLAB. You just put in the number, you push log, it's done. You don't need to worry too much about that, okay? And so and then x can take on different values, x1 or x2, heads or tails. And so you need to sum over all the states. You put in probability 1, log probability 1, probability 2, log probability 2. You put in your 0.5 for all those probabilities because they were equal. You do a little bit of algebra, and at the end you come out with the answer, 1. The answer is 1. And now, since the log here had base 2, the units of entropy are bits. And so probably you've all heard about computers and maybe a binary code of some sort, and you have a bit, and a bit can be 0 or 1, right? And so 1 bit can represent 2 states. And just like in this situation, we had 2 states originally, each equally probable. So the uncertainty is 1 bit of uncertainty. Okay? Now, if you happen to not have equal probability in each of these coins, say you had slightly more probability, 75% for heads and only 25% for tails, clearly that coin toss, there's less uncertainty. You can guess that it's going to be heads a bit more than tails. So there's less uncertainty. And if you calculate the entropy in these with a different combination of probabilities, the entropy goes down. And it's maximum when the uncertainty is maximum, which is what you want because it measures uncertainty, right? And so if either one of these states had a probability of 1, then the other state would have to have a probability of 0. And then you would say, well, there is no uncertainty. If I toss a coin with the probability of having heads of 1, it's going to be heads. You don't have to be a genius to figure out what to bet on here, right? And so the entropy measure also goes to 0 for those 2 conditions, okay? So it does what we want it to do. And for a probabilistic event with 2 outcomes that are equally probable, the entropy is 1 bit, okay? But now let's say we're going to toss a coin twice. Conveniently, with a coin toss, what's going to happen on the second toss is completely independent of what happened on the first toss, okay? So it doesn't matter at all. Now, if you want to say, what's the probability of getting heads on the first toss? It's 1/2. What's the probability of getting heads on the second toss? It's also 1/2. It didn't change. But so what's the probability of getting heads and heads? So you multiply the two probabilities together. Everybody probably knows this. Getting two heads in a row is 0.5 times 0.5. It's less probable, right? And so, but the interesting thing is entropy actually adds. So if you had one bit of uncertainty in the first coin toss, you still have one bit of uncertainty in the second coin toss. And so for two coin tosses, you have 2 bits of uncertainty. Okay? And so if probabilities multiply but entropies add, and the equation for entropy has this funny log, this is why. Because now if you say, well, P now, instead of just one event, we have 2 events. So P is P1 times P2. But you put that in a logarithm, then the logarithm, it has this nice property that the log of P1 times P2 is the log of P1 plus the log of P2. So it gives you that additivity that we know intuitively entropy should have. So entropy actually has to use this equation to describe it. Okay? And we see that it works. It makes sense in this nice simple example. Now we want to try and apply it to a slightly more realistic example or a useful example of, say, a neuron. And this is going to illustrate the concept of conditional probability, which I think has already been mentioned briefly in a previous talk. But so let's just imagine a fake neuron now, which still takes a stimulus and gives a response. But now there's only 2 possible stimulus and 2 possible responses. Sort of like a coin toss. You could have 2 possible states, right? And so in a perfect world, maybe stimulus 1 would always cause response 1, and stimulus 2 would always cause response 2. But you could imagine the opposite extreme, where stimulus 1 could cause either response equally probably, and stimulus 2 could also cause equal probability of response 1 or response 2. This is just kind of a toy example to help illustrate the point of entropy and get towards information. Okay? So let's just imagine a set of probabilities that it's kind of just made up here, but just for the purpose of illustration. So now the joint probability distribution is for the probability of getting a stimulus and a response. So there's 4 different combinations now. So there's 2 stimuli, 2 responses, which gives 4 combinations total, right? Stimulus 1, response 1, stimulus 1, response 2, and so on. And let's just imagine they have this particular distribution of probabilities. Okay, the probabilities have to sum to 1. Just means that your probability distribution is normalized. But now we want to see, what are the conditional probabilities here? So we could say, what's the probability of the stimulus given that we have R1? So this little vertical bar here means given or conditioned on the fact that we know what happened after the bar. Okay? And so if we just look at our little table here, we say, okay, we know we got response 1. Let's look here. Okay, so we have equal probability of either stimulus 1 or stimulus 2. Here they're noted as a quarter, but once we renormalize, that would be probability 1/2, probability 1/2. So given that we have response 1, there's 2 possible states that it could have been. Both are equally probable. So we don't even need to use a formula to calculate the entropy. You know what it was from the previous slide with the coin tosses, right? You have 1 bit of uncertainty given that you know the response is R1. Okay? But now what's the conditional probability distribution of the stimulus given that we have R2? So if we look here, R2, well, and it says that the stimulus has to be S2, and it's definitely not S1 at all. Right? Of course, this is a toy example made to work this way. But then the probability distribution is 1 and 0. There's no uncertainty anymore. We know exactly what the stimulus has to have been. So if you calculate what's the conditional entropy from the conditional probability, now it's 0 bits. So there's no uncertainty anymore. At the very beginning, maybe, before we even looked at response 1, we could say, what's the probability distribution of the stimuli? So actually, the probability distribution is stimulus 1 is only a quarter, stimulus 2 is 3/4. So the entropy of the system initially isn't 1 bit. It's a little bit less than 1 bit. And so if we observe response 1, we're actually even more uncertain now about which stimulus it might have been. So the uncertainty went up. But if we observe response 2, now we know exactly which stimulus it was, where before we observed any responses, we didn't know anything, or we knew a little bit less. So the uncertainty, by making an observation, has reduced. Okay? And so I hope you can sort of connect the dots here a little bit and piece together where I'm going with this. But you would say if we observe R2, we've gained information. We've learned something, right? So information is kind of a reduction in uncertainty or a reduction in entropy. It's really a reduction in uncertainty. Entropy is just a fancier word for uncertainty. Okay? So now we're going to just sort of step it up a little bit more and make a slightly more realistic neuron model. Yep? Is there yeah, you could calculate the information. You could calculate the information transmitted by this neuron if you wanted, just using all these values here. But we haven't actually reached the equation for information yet. We're just building up to it. Yeah, that's coming up sort of on the next slide, I guess, the actual equation for information. But we're just starting off with entropy and entropy reduction, which, yep. This part? Yeah. Yeah, it probably does. Yeah, that's, I think, just a typo. Yep. Oh, okay, okay. So if we observe a response, we know that the stimulus still has to be S1 or S2, okay? And so if we observe R1, this just tells us that it's equally probable between these two states. But the conditional probability distributions still have to be normalized because we know S has to have a value. It can either be S1 or S2, right? So for the joint probability distribution, P of R comma S, the probability of all states has to sum to 1. But for the conditional probability distributions, you would renormalize it so that this column has to sum to 1, or this column has to sum to 1. Or if you wanted to do it, conditional of R given S, then you would have to redo it so that this row sums to 1, or this guy sums to 1. Okay? No problem. So now we're going to talk about a slightly more realistic neuron model here where instead of just having 2 possible inputs and getting 2 possible outputs, the input value can take on some sort of continuous, it's a continuous variable, right? A real number. It can maybe have a range that's finite, maybe have a range that's infinite, depending on your system, okay? And then the output, let's just say it's just a firing rate for now. We're not going to worry about the actual spikes. And the firing rate can also take on some continuous values. And don't worry about it too much, but the firing rate can't be negative, and it probably has some maximum value. It can't fire infinitely fast, but that's just a property of neurons, not a property of information theory. But so this is going to be the neuron's tuning curve, this color map here, where so if we give an input stimulus of a certain value, we're going to get an output firing rate of a certain value. And there's going to be a deterministic component here, which is kind of like your tuning curve. So the response is a function of the stimulus. This deterministic component gives me this sigmoidal shape here. But then there's going to be a stochastic noise term, which the noise could maybe vary as a function of stimulus, but let's just assume the noise is constant for as a function of stimulus, and it's a Gaussian noise distribution. Okay? So now, instead of, if this was just deterministic, this thing here is probability. So red is higher probability, blue is low probability, right? And so if it was just deterministic, you would just see a thin red line in a sigmoid like that, right? But since there's a bit of noise, for any particular stimulus value, the response will take on a distribution of values, okay? And if you give your stimulus, and you give stimulus values from this distribution, and you give it for a really long time, and you keep collecting all the response values that you get, and then you make a histogram to make the probability of the response, you're going to get a big distribution like this. Okay, and that's just the response distribution using all possible stimuli. But now let's say, what about these particular values of the stimulus? So if the stimulus value, say S1 was here, you would go up here and you'd say, okay, so the response has to have a probability distribution like this, okay? And so we project that over here. This is the conditional probability distribution of the response given that we had stimulus 1, okay? And these things still have to be normalized, of course, and the black curve has also got to be normalized. So for any different stimulus value that you take, your response could take a distribution of values, okay? And so for this full response distribution, we could calculate the entropy of that distribution. It's got some uncertainty, which is basically how broad is the distribution. The broader it is, the more uncertainty there is, so the entropy is higher. But then for any particular stimulus, the distribution is actually narrower. So the entropy, or the uncertainty of the response for any particular stimulus is much less, okay? And so you can use the same equations as before to calculate the entropy for each of these conditional distributions, and you would do that for all possible stimuli. And then the actual amount of information that the neuron is going to transmit is going to be the total entropy of the response, which was the black distribution, which was for all possible stimuli. But then there's this term here called the noise entropy, which is basically just the conditional entropy for each of these conditional distributions times the probability that that stimulus actually occurs. For instance, S3 has a very high probability. Over here, there's almost no probability, right? And so then you're going to add up all those conditional uncertainties weighted by the probability of those stimuli. And this term is called the noise entropy. And we're going to subtract this entropy minus this entropy, right? And so this entropy, it has a negative sign, and this one had a negative sign too, but because of this negative sign, it gets canceled out. And so the reason it's called the noise entropy is, you imagine if your neuron was deterministic, for each stimulus, the response distribution wouldn't be a broad Gaussian like that. It'd be very narrow and maybe approach a delta function, right? And then if the delta distributions get really, really skinny and their entropies go towards 0, and so this noise entropy term will go towards 0. And so if the noise is low, this term is small, and so this term minus this term, if we're subtracting a small thing, the information is big. If the noise gets higher, this term gets bigger, and then the information is going to get lower. Yep. No, this is just... Right. So just imagine your stimulus is some sort of time-varying signal, and it's drawn from a Gaussian distribution, right? So their stimulus we would still consider it a time-varying signal, but then this is just the probability distribution of the values that it takes. Okay? We're going to kind of get to that a little in the next couple slides. And really, that's what you want to think about when you're looking at neural coding. But it's easier to start off calculating entropy and information just using probability distributions. Once you get to the time-varying signals, it's going to get slightly more complicated. But hopefully, we can get there and not take too long. But so, in the first, with the fake neuron, we saw that sort of there was an uncertainty in the stimulus, but then once we observed a response, the uncertainty was reduced. Okay. But you can flip that around and say there's an uncertainty in the response, but if you present a certain stimulus, the uncertainty in the response is reduced. And so you can calculate actually information either way. The information between R and S, the response and the stimulus, could either be the response entropy minus the conditional entropy of R given S, or the stimulus entropy minus the conditional entropy of the stimulus given R. Or even this funny extra term here, the response entropy plus the stimulus entropy minus the joint entropy, which we didn't actually talk about, but they're all equivalent. And so if you switch, what's the information between S and R? It's the same as the information between R and S. It doesn't matter. It's symmetric in direction here. And this little Venn diagram here is just supposed to help you remember the equations for entropy. So one big circle here is h of x, here is h of y, but the information is really just the overlap of the two, right? So you could say h of x minus this h of x given y, this little Pac-Man shape, and you get left with the information. Okay? So the equation for information is a reduction in entropy due to making an observation, or the presence of a stimuli. But if we just write out those equations, so there's the minus sign, there's the not minus sign, you just write it out, and you use Bayes' rule, and you do a little math, and you manipulate it around. You can write it down into a form like this, where now we're just looking at the joint distribution between stimulus and response. And then there's the stimulus distribution and the response distribution. And so you could say, if the stimulus and response, these two random variables, are independent completely, then the joint distribution just equals P of R times P of S. They're independent. And then P of R times P of S divided by P of R times P of S is 1, and log of 1 is 0. So the information is 0 if the stimulus and response are independent from one another, which is what you would intuitively expect, right? If you give a stimulus and the response is completely independent of the stimulus, it's obviously not going to tell you any information about the stimulus. And probably you don't actually have a cell. You know, if you put your electrode into a brain and try to give a stimulus and the response is not responding to the stimulus, you keep looking until you find something that does respond to the stimulus. And so now using this formulation for the information, you can actually, it has this nice advantage that you can write information of R between R and S, but still as a function of S. So now instead of just saying, well, the total information transmitted by the stimulus to the response is 1 bit or 10 bits or however many bits, now you can actually see how much information is transmitted by different stimulus values. Okay? And so one common sort of an achievement of using information theory here is if you had some tuning curve that was just, it started off low and it went high, and so the neuron is firing its maximum firing rate for these stimulus values over here between 8 and 10, right? And so you would say, well, that's the neuron's preferred stimulus. That's what causes it to fire the most. So that's obviously what's going to transmit the most information. But that's actually not true. And according to information theory, the stimulus which transmits the most information is sitting right here in the middle of the tuning curve. It's not at the maximum value of the firing rate. It's actually at the maximum value of the slope, sort of in between the two extremums. And so finally, to kind of bring it back to real neurons and what everybody does in the lab, you present a time-varying signal, and you get some response, which hopefully looks a little bit like your stimulus, so that you know the response is related to the stimulus. Okay? But first we're going to just say, imagine you get a stimulus distribution. So this looks like a sine wave, and this is a Gaussian. Just let your mind accept that. Okay? Don't worry about it. If it's a Gaussian, everything is really nice because the Gaussian is described by its mean and its variance. And so the entropy of a Gaussian, or its uncertainty, is just a function of its variance. So it's really simple to calculate the entropy of a Gaussian, except you have to do a bit of calculus, but it's intuitively easy, okay? And so now, if your neuron just takes an input that's a Gaussian distribution and you add some noise to it, and you get a response, but now you've added this Gaussian noise, and you might say, well, I can see the signal from the stimulus in there. It's modulating. I see a signal, but I also see a lot of noise, right? And so you might hear about this term called the signal-to-noise ratio. How much signal is there and how much noise is there? If the noise gets so high that you don't see the signal anymore, then the signal-to-noise ratio is really low. You don't see any signal. You can't. It's just too noisy, right? And so if you actually just plug in a Gaussian stimulus input and a neuron that adds Gaussian noise to the stimulus, and you use those big equations on the previous slide, it only takes a couple pages of calculations, and you can get a result here which says that the information is equal to the log of 1 plus the signal-to-noise ratio. So the variance of the signal that you can find here and the variance of the noise that got added to it. Okay, and so how exactly you're going to calculate that and estimate that for real neurons and real systems is what Ashkan is going to talk about in a couple of seconds here. But I just want to make one extra point, that when you're looking at these time-varying signals, and this is the reason why I don't start looking at the time-varying signals, okay? But so if you look at the response, and it fits in a probability distribution. So at one point in time, the value that you get in the response comes out of a distribution which has a certain entropy or uncertainty. But at another point in time, your value is going to come out of a distribution again that has another entropy or uncertainty. And so because entropy adds, if we make this time signal longer, we're adding more time points. Each one adds more entropy. So if you want to calculate the entropy of a spike train or the entropy of some long time varying signal, it depends on the length of the signal. So if the signal gets longer, the entropy goes up. And so this is kind of a problem for neuroscience because we don't really want to get a result like that, right? And so the solution to this is to consider the entropy rate, how much entropy per second is there generated by the neuron or coming out of the signal. And so when you're looking in the papers and the literature, you're going to see that information is usually reported as information per second or bits per second, not just bits. And since you know that a neuron is going to fire action potentials or spikes with a certain spikes per second, you can convert this to get information in bits per spike and see, does one spike really carry any significant amount of information, or is it really just the firing rate and sort of a collective phenomena with many spikes contributing to the information? And with that, I'm going to pass the microphone off to Ashkan to tell you how to actually calculate and estimate these values of entropy rate or information rate in real neuron systems.